One thing I think we'll all agree on is that in thermodynamics, there are lots of variables: internal energy, entropy, temperature, pressure, volume, chemical potential, number of moles, heat capacity, ideal gas constant, and even new stuff like enthalpy. Before this zoo gets too big, we're going to take some time to work on classifying and understanding a bigger picture of how these variables fit together, how they're related to each other, and some topics about the minimum amount of information that's necessary to actually define a thermodynamic system or model. Before we do this, we're going to cover some mathematics that's really necessary to be productive in this section, and it's the mathematics of what's called differentials. Now, we have been implicitly using differentials already in this course when we write a quantity like du, dw, or dq. That's in the first law of thermodynamics. Putting a d in front of a quantity is called a differential, and the concept behind it is an infinitesimal change in that quantity. But now we're going to make this a little bit more exact. Let's consider a space where there are variables x, y, and z. And the idea is that other variables like a could depend on these. A differential, dA, is something that we can express as a linear combination of the independent variables in the system. So we have dx, dy, and dz multiplied by some coefficients, the lowercase a's with the subscripts. These lowercase a's with subscripts could depend on x, y, and z themselves. There are an important class of differentials that are called exact. And an exact differential is one that, in essence, has an underlying function or an underlying quantity that represents its value that's changing. The necessary and sufficient condition for a differential to be exact is that these coefficients, the lowercase a's, must be possible to write as partial derivatives of that function. So in order for a differential to be exact, there must exist a function of the independent variables that has the following property. The partial derivative with respect to x with y and z held constant gives this ax coefficient here. The partial derivative with respect to y expressed in terms of x, y, and z gives us this coefficient here, and the partial derivative with respect to z with x and y held constant gives us this coefficient here. So that means that if a differential is exact, we can express it as dA equals partial of a with respect to x dx plus partial of a with respect to y dy plus partial of a with respect to z dz. Now, we're not guaranteed when we write a differential out like this with arbitrary small a's that a function like this actually exists. Let's look at two examples. let's do an example where the dA is set up as 8x minus 3 over y times dx plus the quantity 3x over y squared times dy. Now, this is totally sensible if we have a certain current value of x and y, and we have small changes in the quantities x and y. We can approximate the change in the quantity a by just plugging in those. Now, formally, we don't associate a value with the differential. It has an infinitesimal size approaching 0, but we can approximate what it means by plugging in just small changes, like turning these d's into deltas gives us something that's correct to first order. Now, if we look at these two functions here, we can identify what we're seeing. The lowercase a sub x is this first term in parentheses, 3 over y, 8x minus 3 over y, and the lowercase a sub y is 3x over y squared. So the question is, does a function capital A exist that has the property where its derivative with respect to x is equal to 8x minus 3 over y, and its derivative with respect to y is equal to 3x over y squared? Does such a function exist or not? Well, one thing that we can do to check, and this turns out to be a sufficient condition, is if we take the derivative of this entire equation with respect to y. So form the quantity second derivative of a with respect to x and then y. What we get on here is 0 for the first term and plus 3 over y squared for the second. If we do the same thing over here, take the derivative with respect to y and then x, what we'll do is take the x derivative of this side, we'll get 3 over y squared. Now, we know from the rules of calculus that when we take derivatives of a function of multiple variables, the order of those derivatives does not matter. So if a is a real function that exists, then these two derivatives with respect to x first then y, and then with respect to y first and x, should give us the same value. In this example, they do give us the same value, and that means that this function a does exist. Let's try to find out what it is. We'll do this by solving these partial differential equations. These are not too hard to solve, but it's good to go through the technique at least once. So the first equation here, which I'll write as 1, implies that a is a function whose derivative with respect to x, treating y as a constant, is 8x minus 3 over y. So that means we know a little bit more about the function a. If we take the integral of this side with respect to x, we're going to get 4x squared minus 3x over y. Remember, we treat y as a constant. The catch here when we solve an equation with partial derivatives is that this only determines its dependence on x. The function a could have any other function added here which depends on y, and it would still solve this equation, because when we take the derivative with respect to x, portions down here which depend on only y all turn to 0. So we'll write this as this part, which is the dependence on x, plus some other unknown function which now must depend only on y. Okay, so that's part of the solution. We can now take this partial solution and compare it to the second equation. First, I'll take the derivative of this partial solution with respect to y. I'll get 0 for the first term, because it only depends on x. For the second term, I'll get positive 3x over y squared using the power rule. And for this third term, I'll get the total derivative of f with respect to y, because f only can depend on y. Now let's compare that to our differential equation up here that we have to actually solve. This one says that the partial derivative of a with respect to y must equal to 3x over y. So comparing our partial solution here to the exact value of this derivative, and we see that these two terms, luckily containing x, both cancel, and we get this equation reducing to say that df dy is equal to 0. So the function f, this arbitrary function that must depend on y only, actually turns out to be an exact constant. So f must be a constant. So we'll call this, for a good reason, we'll call this a0. So that's a constant, does not depend on x and y. Notice that we're kind of fortunate here in our solution that all the terms involving x at this final step canceled on both sides. Right? If that doesn't happen, then the function a does not exist. It can't exist. So let's write our function a here for our final answer. It will be our temporary solution with the correct value of f function plugged in. So 4x squared minus 3x over y plus an undetermined constant. Okay, so you can check this now, go back here. Is the partial with respect to x equal to 8x over 8x minus 3y? Yes. Is the partial with respect to y equal to 3x over y squared? Yes. So we found the solution, the most general solution to this exact differential. Now let's look at a second example where it doesn't work out so well. Let's define b as a differential equal to y squared dx plus x minus y dy. This is completely legal. At the current value of x and y, we could imagine a small change in x, a small increment in y, and find out how much b changes from that. But does a function b exist? Our intuition here is like, of course the function exists. How could it not exist? But let's go through the actual logical mathematics and see what happens. First, we'll identify the bx, lowercase b with an x subscript, is y squared. And the by is this term here, x minus y. Let's check our condition to see if a function capital B could exist. If we take this derivative here, we get 2y. And if we take the derivative of this coefficient with respect to x, we get 1. Now those aren't the same, and they can't be the same unless y has a specific value, which is useless. So we expect that this function does not exist. But let's push along with the plan of solving these differential equations and seeing where it goes wrong. Okay, so let's assume the function b exists, and we're looking for a function capital B where its derivative with respect to x is equal to y squared, and its derivative with respect to y is equal to x minus y. Let's try to solve this the same way we did for the function a in the last example. First, I'll take this equation for the derivative with respect to x. I know that this tells me that b must be equal to y squared times x plus some undetermined function of y. That's the most general solution to this equation. All right. Now I'll go in my second step, take the derivative of this partial solution with respect to y. I'll get 2yx plus the total derivative of f with respect to y. And now that's supposed to be equal to x minus y. right? So if I rearrange this, I will find an equation that looks like the total derivative of the function f with respect to y must be equal to x minus y minus 2xy. Now this is where we get our contradiction. The function f is only allowed to depend on y, but we have x's sitting over here that don't cancel. That means for different values of x, we might be able to get a solution for a specific value of x, but going to a different value of x makes that solution wrong. So we can't possibly find a formula for f that depends only on y that makes this equation solved no matter what the values of x and y are. So we say there is no solution here, and therefore we come to our contradiction. Our assumption that the function b existed is wrong. So no function b of x and y exists. So what does this mean in practical terms? When a differential is exact, there exists a function that goes along with it that sort of stores its value. So when we integrate from some initial condition 1 to some final condition 2, small changes in the quantity a, what we're actually doing is we're ending up with the difference between the function at the final state minus the initial state. But if we try to do the same thing with an inexact differential, no such function exists. This integral has a value, but we cannot associate it to the change in some underlying quantity. In essence, the value of this integral depends crucially on the path that is taken to get from state 1 to state 2. It can't just be associated to a difference at the endpoints. So in thermodynamics, we know that quantities that are state variables exist as functions. They have a value which is independent of how they got there, right? So you look at a system, it has a temperature, an entropy, a volume. If someone else comes and does some messing around with it and returns it to that temperature, volume, and entropy, then it will have the same values of those quantities, right? There'll be no overall change. But there are, in fact, quantities we've been using quite a lot that are inexact differentials. The two main ones are heat and work. We know, actually recently from our work on engines and refrigerations and cycles, that if you take a system at some starting point and go around some path in the allowed space and return it to its initial point, it can have like a total amount of heat absorbed that's greater than 0, and a total amount of work output that's not 0 also. So if you start at if you start in some initial condition, go do some path, return to the same condition at the end, all of these exact differentials would have no overall change. But the inexact differentials can accumulate some value. So there's no way to assign like a particular value of heat to a spot, say, in the PV diagram. If we go on some cycle and come back to that same spot, we'll have increased our, absorbed some net amount of heat, and then we've got two heat values for the same spot, so it's inconsistent. So mostly what we want to work with in the forthcoming sections are exact differentials. We're going to talk about the relationships between energies, state variables, and response functions. And we're going to avoid inexact differentials because they basically don't behave as nicely in terms of calculus and doing integrals with them and stuff as the others. So now let's focus on these exact differentials. And derive some identities that can relate them to each other. And we're still going to do this in the abstract for now, but we'll do some examples to show what all of this notation means. So let's begin by imagining some function a exists which depends on independent variables x and y. So we can write dA, the differential change in a, as partial of a with respect to x, well, y is held constant, times the differential of x, plus dA dy with x held constant multiplied by this is multiplied by dy. Right. Okay. Now suppose that we introduce a fourth variable here, in addition to a, x, and y, called z. Suppose z exists as another exact differential, and y is thought to depend on z. So y is a function of x and z. So therefore dy, since it's another exact differential, could be expanded in terms of its partial derivatives in the same way. Now this is just all abstract. The way we're going to get our identities that we'll be able to apply are by realizing that we can now take our expression for dA and try to eliminate the dy, right? Y was supposed to be a function of z and x, so maybe z and x are the real independent coordinates in this system, and we'll get rid of y by plugging in this whole expression in these square brackets. So dy dx and dy dz. So that's what we get for dA. Now, this is all totally consistent. There's nothing really going on here. But where we're going to get our identities from is realize now that this is an expression for dA in terms of dx and dz. So let's rewrite that here just at the bottom and collect these terms. So the ones that are multiplied by dx are the first one and the product of these two. So dA dy with respect to x and dy dx, with z constant there. So that's what multiplies dx, and the thing that multiplies dz is this outside times that inside the brackets. So dA dy x dy dz x, that multiplies dz. All right. Okay. So this is an expression for a in terms of a coefficient times dx and a coefficient times dz. And a, x, y, z, these are all exact differentials. Now if we turn back to the definition of the exact differential, we notice that now it's like our ax is just this thing in square brackets, and our az is just the product of these two here. So since a is an exact differential, in terms of x and z, the partial of a with respect to x while holding z constant is equal to the things in this square bracket. So dA dx y plus dA dy at x dy dx at z. So there's one identity. Let's just put a pin in that one, come back to it in a bit. The other one is dA dz. So this one up here is AF, right? And this one up here is lowercase a subscript z. So this is dA dz at constant x, and that's equal to dA dy at constant x dy dz at constant x. So I'm just collecting those terms there and writing that to dA dz. So these are two identities that are satisfied by any four quantities that are exact differentials. So when we go later on to use this in the context of thermodynamics, A could be enthalpy, X could be pressure, Z could be temperature, and Y could be volume. And you could make all those associations and you'd get an equation that was a true relationship between those quantities. It's kind of impressive. Now let's try to interpret these a little bit. Let's look at the one on the second line here first. If you recall your calculus, you'll notice that what this equation is basically doing is taking the dA over the dz and splitting it up with a dy in the middle. So this is the chain rule. And on the slides, I listed this as number 1 because it's the simplest. It's probably one that we've seen before. So we have some additional variables going on here. There's A, Z, A and Y, Y and Z. We also have this X hanging around here. And what this X is doing is it's basically just sitting there reminding us that X needs to be kept constant in these derivatives. The one on the first line here is probably one that we haven't seen before because it doesn't really become necessary unless you're doing calculus for functions that depend on multiple variables. So what are we doing here? On the left side, we have the derivative of a with respect to x. And on the right side, we also have the derivative of a with respect to x. The difference is this one has z held constant, and this one has y held constant. So the application we're going to find for this is when we have a derivative which specifies a certain variable to be held constant that's inconvenient, we can change that to hold a different variable constant at the expense of adding on some other terms. So we call this one change of variable. And we'll label it as identity 2. This one can look like a big jumble of letters the first time you see it, but there is a pattern to it that I use to remember it. If I start off with what's over here, and these could be any 3 variables, remember, the next term on the right-hand side is the same derivative with something different held constant. Okay, so this could be like we want to do the derivative of energy with respect to volume. Well, entropy is held constant. Well, that's annoying. So instead, we'll do the derivative of energy with respect to volume. Well, temperature is held constant, and that's easier. But then we have to do these other terms here also and add them on to make it actually correct. So here's the mnemonic. These first 2 have the same derivative with only a change in what's held constant. The next term here, so the third derivative from left to right that appears, is the same as this one with the 2 variables at the bottom swapped. So here we have xy, in this one we have yx. And then what's multiplied by that is what's necessary to make it look like a complete chain rule. So we're doing dA dx, and here we have to have dA dx with the dy's in a canceling position. The variable which held constant on the last one is just the original variable that was held constant at the front. So that's how I remember that change of variable rule. You might find that to work, or you might just memorize it or write it on your note sheet. Okay, so those are the two essential identities, and they're completely general. Any variable could be plugged in for any one of these spots. We could even plug in, say, the same variable for two places on here, like let a equal x or let a equal y. And we'll get other simpler but true identities. There are two of those that are valuable to remember. The first one that I'll write out is in equation 1, let's let a equal z. Still should be valid. So if we have a equal to z, then this derivative here on the left is equal to 1, no matter what we held constant. In the first term here, I just replace a and z. The second term doesn't change at all. All right, so that tells me that the product of these two derivatives is equal to 1. And we notice what these are is they're just the inverses of each other. So this tells us for exact differentials, we have a relationship where if we want to take the derivative of z with respect to y, and maybe for some reason that feels awkward to us, like the derivative of temperature with respect to entropy, that feels awkward, right? Usually the more complicated variable is on the one you're taking the derivative of, and the simpler one is the variable on the bottom. So if this derivative feels awkward, we're totally legally allowed to replace it by the multiplicative inverse, 1 divided by the derivative with y on the top and z on the bottom. Okay, so this might seem like it can be weird in some situations that you can just change a derivative like this by putting it on the denominator of a fraction, but it actually does work out as long as these variables are all exact. So this one we'll label as rule 3, and we'll call it the inverse rule. So we don't really need the full power of the chain rule. We can do a simpler version of it with just two variables or two derivatives. Call that the inverse rule. Okay. The last one that we'll actually give a name to is going to follow from identity 2, the change of variable. Again, we're going to take that equation and let z be equal to a. Let a be equal to z. That's probably the more appropriate way to write it out. So we'll plug in that everywhere here. In the first term, now be attentive. If a is equal to z, then we're taking the derivative of z with respect to something, well, z is held constant. So if z is held constant, it's not changing at all. That derivative becomes a big 0. So on the left, we've got 0. Then on the right, we're going to have dz, dx, and then dz, dy. And the last term here doesn't change. dy dx with respect to z. So this identity only involves 3 derivatives instead of 4. It looks a little weird right now, but I can rewrite this in a way which makes it easier to remember. What I'll do is just move these things around using algebra and the inverse rule, and what we'll get is dx dy with z held constant times dy dz with x held constant times z dx with y held constant equals -1. So if you want, you can pause and try to see how I got this from just kind of moving these around algebraically, flipping them upside down and stuff. So this is a neat rule, number 4. We call this the triple rule. So it relates any 3 variables. And a nice way to remember this one is the variables go in a cyclic alphabetic order. So we have x, y, z. Then we cycle them one direction. So then we have y, z, x. We cycle them once more, so z, x, y. The product of those 3 always comes out to be -1. So usually we use this by, we have a derivative that looks like dx, dy with respect to z, held constant, and we don't like holding z constant. We'd rather have z be one of our variables in the derivatives. So we write the product of these 3, and then we end up, moving these to the other side, maybe using the inverse rule to write these second 2 derivatives as negatives on the right side of the equation to eliminate the dx y with z held constant that we didn't like. Okay, so those are the 4 identities that we'll use to relate these differentials to each other. Now I realize that's been quite formal. We just have lots of variables floating around. Let's try to get a more visceral feeling for what these things mean. I'm going to show 2 slides here that give you a feeling for what these mean. The first one has a function a as a function of x and y that's equal to x to the 4th times y squared, and a function z which is equal to x times y. Now on this 3-dimensional plot, we see the a as the vertical axis. The x and y are the 2 horizontal axes in the horizontal plane, and it kind of curves upwards as x and y increase. We have a set of lines there, though. The black and red lines are lines of constant x and constant y. So those are just grid lines, right? They align with the axis. The lines in blue are lines of constant z. So what's being shown on this graph is that a has a value at specific x and y. Z has a value at a specific x and y. But if we follow one of these black, red, or blue lines, we see that we get a totally different path, a totally different dependence of a if we move while x is constant versus if we move while y is constant versus if we move while z is held constant. We go along totally different paths in that xy plane. The second graph I'm showing here is a plot of a versus x with different things held constant. At first, you can see a versus x with y set to 1 and y set to 2. Obviously, those are different curves. But the interesting thing is the 2 graphs where we have a versus x with z set constant to 1 and z set constant to 2. And you can see that those are totally different curves with different slopes. So when we do these derivatives, where there's multiple variables, it's just as important that we take the derivative with respect to the right variable as it is to know which variables are being held constant. If we do dA dx, the slope of a on this graph, holding y constant versus holding z constant gives us a totally different answer. Now that you have the visualization of what these functions look like, let's test out some of our identities. First, we'll just get some practice doing derivatives and record these so we can use them later. Okay, so dA dx with y held constant. Well, here's the expression for a. Y is right there. It's in the formula, so I can guarantee it be held constant, and I'll just do the derivative with respect to x. So 4x cubed times y squared. The second row here, dA dy with x held constant x is just treated as a constant, so I'll have x fourth times 2y. Okay. Now let's do some of the more interesting ones. Let's do dA dx while holding z constant. Now there's one very simple way to do this, which always works in principle, but might not always be easy to do in practice. It's to write our expression for a in terms of the variables x and z, instead of in terms of x and y. So let's see how that goes. Well, we want x to be in there, so the x to the fourth can stay. But we don't want y, we'd rather have z. So instead of y squared, I'll write y as z over x. And that was y squared in the definition of a, so here it will z over x squared. So a, written as a function of z and x, is x squared z squared. And then I can do this derivative because I'm guaranteed to know what x is doing and what z is doing. So I'll get 2x z squared for dA dx with z held constant. And for dA dz, with x held constant, I'll get 2x squared z. All right, so we can check between these, right? Like dA dx with y held constant and dA dx with z held constant are totally different formulas. Even if we plug in, z is equal to xy, we get 2x cubed y squared instead of 4x cubed y squared. All right, so let's ask another question here with this example. Let's challenge ourselves. See if we can figure out the derivative of a with respect to y while z is held constant. You can pause the video for a moment and try to see if you can work out what this is. We're going to do this in 3 different methods. It's somewhat overkill. The first method is just to take a and try to solve it in terms of y and z. So that would give us a equals z to the fourth over y squared. And then we just take the derivative of this, holding z constant. So we get dA dy with z constant equals to negative 2 z to the fourth over y cubed. All right, very good. That works. However, when we deal with more complicated variables like entropy, temperature, pressure, it might not always be possible to solve or rearrange the stuff on the right-hand side to be just in terms of y and z. Even if we can't do that, like with algebraic manipulation, we're not at a total loss because we have these other identities at our disposal. So let's do method 2 here. We'll use the chain rule to do this derivative. And the chain rule here, we would need to find a fourth variable. It's going to be x, that we can sort of wedge in between this derivative of a with respect to y. Okay, so dA dx with z held constant is something we already calculated up here. That's 2x cubed y squared. Dx dy with z held constant is something new that we need to get. So x in terms of y and z would be x equals z over y. So the derivative of x with respect to y is minus 1 z over y squared. Okay, So if we do that, we multiply these together, we get negative 2 x cubed z. And if we plug in for x as z over y, then we get z to the fourth over y cubed. So we get the same thing there. We're going to do this in one more way using the change of variable rule. Okay, so this rule is based off of saying, gee, I really hate holding z constant. Can't I just hold x constant instead? I mean, I already know what that one is. And yes, for part of it, but we still need to work out the terms that are added on here. So we have dA dy with z, turns into dA dy with x, and then I know the second term here is going to be dA dx with y, reverse the bottom numbers, and then it's got to be dx over dx to match this dx over dy to match the original derivative, and held z constant to match the original derivative. Okay, so let's see how this one works out. dA dy with x was 2x fourth times y. dA dx with y was 4x cubed y squared. And dx dy with z held constant, we just did this one on the last line, that was negative z over y squared. So we'll have minus z over y squared. And that one, we can simplify this a bit here, just bear with me as I erase on the board. The y squareds can be canceled, so we'll get that. We can replace the z's. Let's replace the z for an x. So we'll replace z with xy, so it'll be x fourth y. So we'll get minus 2x to the fourth times y. And that's the same as these other ones. So we've got minus 2z to the fourth over y cubed is the same as minus 2x to the fourth times y. So all three of these methods give us the same answer. They better do that because they're supposed to be identities. But depending on the situation, when we get into more complicated formulas for the a's and the z's and so forth, one of these methods might be really simple to do. The other two might be horrendously complex. So it's good to know all three are available. Let's try one more derivative that might seem quite bizarre. The derivative of x with respect to y, well, a is held constant. Now this seems like a weird derivative for us because we think of a as the function. But the beautiful thing about exact differentials is that they don't really care whether they're treated as the result or the input. They're all kind of on an even playing field. So this derivative is perfectly well defined. I want you to pause the video and see if you can find some way to calculate this. You can use any of the identities that you want, or another method if it occurs to you. Okay, let's check our work. The answer to this derivative is equal to negative x over 2y. Here are some methods by which you could get that. The first is to use the cyclic rule. This is usually my first recourse when I see something held constant in the subscript that seems inconvenient. So by cycling here, I can move the a out of the subscript and into the derivatives. So I have x, y, a. The next term will be shifting them all up one. So y, a with x, and then a, x with y. And that is, as an equation, is equal to negative 1. Okay, so after that, I turn this around and move the second two product to the other side. So I'll have dA dy with respect to x, minus sign, and then I'll divide both sides, dA dx with respect to y. Okay? So there's our minus sign from the identity, dA dy with respect to x. We already did that one before. It was 2x fourth y. dA dx with respect to y was 4x cubed times y squared. And if we simplify that, we're going to get x on the top and 2y on the bottom. So we get the same answer. Okay, that's not the only way to do this, though. We could have done it by eliminating x, solving this equation for x, right? We could have done this by saying x will be equal to a to the 1/4 power divided by the square root of y. That's valid, and then we can do the derivative of x with respect to y. We'll get the same answer. That works. I find that one to be a little bit undesirable because when you have fractional powers and square roots, there's always kind of a lingering doubt that they might be negative, and you might have extraneous answers and stuff like that. So you kind of wade through this murky area of possible imaginary complex numbers and come out the other side with a correct answer. But it can work. The third way to do this is actually kind of interesting. It's something you might have thought of if you remember doing the exact differentials themselves, right? dA can be written as 4x cubed y squared times dx plus x to the fourth, 2x to the fourth times y times dy. And if we're considering a situation where a is held constant, then the dA will be 0. And we get this equation, which we can now move the two terms to opposite sides of the equation, giving us a minus sign on one of them, and then divide over here by both sides by dy, and divide both sides by 4x cubed y squared. All right, so we get that, and this is only valid under the situation where a is constant. So we get that for dx over dy. And then if we simplify that, the x goes to 1 in the numerator, the y goes to 1 in the denominator, and the 2 and the 4 amount to a 2 in the denominator. So we do get the same thing that way. So if you're new to doing these derivatives, it's not a bad idea to try to do them at least 2 different ways. Make sure you get the same result each way.